Alright, I think this is our last video on friction. I don't know, I say that. we'll see how it goes. I'm planning for this to be my last friction video. Let's work one more example. So let's say we've got, I don't know, some kind of a ramp. Haven't done any ramp problems. Let's do a ramp problem. I don't know why I like this 55-degree angle. I don't really like a 55-degree angle, but this is the second problem now I've had that has got a 1 on it. It's not by design, it just happened. Let's put some block on here. Let's call it 250 pounds. Block on this incline ramp. This block's got a hook on it, and we'll pass a cable over that hook. That cable's going to come out parallel to that. It's also going to be at 55 degrees. So we know what the angle on that cable is. That cable's going to pass over a pulley. This pulley is going to be attached to the ceiling up here in my header up there. And the cable's going to come straight down on the other side. Vertically straight down, we're going to attach to it some weight W. And if the static coefficient of friction is equal to 0.3, that's going to occur here, mu sub s. If that's a 0.3, find W when the 250-pound block just starts to slide. And I should specify up. Just starts to slide up. Because it could go the other way, right? I could have what is the least amount of weight required to hold the block stationary, and that means if there's less than W, and it's going to slide down. That's an interesting problem. In fact, I would challenge you, after we work this one, to stop and then go rework the problem where, okay, find the minimum W to figure out how much, how much weight is required to keep the block from sliding down. We probably won't work that here, but that is a very good practice problem. Maybe a good candidate for a test problem. I don't know. What do we got here? Okay. Well, what do we need? I need to know the forces involved on this 250-pound block. Now, I can draw a free body diagram of this block as it is right now. And if you like it like this, you could say, well, it's 250 pounds. I'm going to have this tension coming up that is 55 degrees from horizontal. I've got a normal force. We'll just call it N. And it is going to be, it's perpendicular to 55 degrees from horizontal, so it is going to be 55 degrees from vertical. That normal force is. And I'm going to have a friction force. It's going to be, the friction is always parallel to the surface that causes it, so it's along this surface here. But it needs to be in a particular direction. Well, I want to pull the block up. That's what the problem statement says, is how much W do I need to add to start pulling the block up? So if this is going up the ramp, that means friction is going to go down the ramp, and that friction is going to be at 55 degrees from horizontal, parallel to the surface causing it. Now notice that is 1, 2, 3 forces I have to resolve. Or if I just rotate this whole thing 55 degrees, is that roughly horizontal? That hurts my brain. And I don't know if this is any better, but that's what I'm going to do is I'm going to take this thing, I'm going to rotate it 55 degrees. And so when I do that, so instead of the weight being vertical, I'm going to rotate the weight 55 degrees from vertical. That's going to be my weight, which is weird. Gravity doesn't do that, right? Well, no, but X and Y, or whatever we want to call them. If you like, you could just draw X this way and Y this way, and just treat it that way. I don't personally. I like to see my I like my x-axis left to right if I'm working in 2 dimensions. So if I do that, if I rotate this whole thing 55 degrees, well, that means this tension force gets rotated 55 degrees. So the tension force is now in the x direction. This normal force gets rotated 55 degrees, so now it's vertical. And this friction force also gets rotated 55 degrees, so now it's horizontal. And now I've only got one force to resolve. Mathematically, these are the exact same. I just find this is less complex. It's a little hard to go from here to here, and this is not weight. This is 250 pounds. Weight is this guy over here. This one's 250 pounds. This is the block we're working with here. So again, I've taken this block and I've just said, instead of putting on this incline, let's pretend that let's say that x is actually this direction, y is perpendicular to that ramp, and let's draw a free body diagram accordingly. And this is pretty easy then, right? Then sum of forces in the x direction, that tension has minus the friction has to equal 0. So that tension has to equal the f direction, the friction force. And sum of forces in the y direction, oh, no, that is not right. I apologize. What did I mess up? What did I do wrong? You catch that? Sum of forces, I'm in a hurry, I apologize. Sum of forces in the x direction, tension minus the friction force, that is correct, but I've got part of this now. So part of the weight, because I've rotated, I'm calling x and y something different. This is minus 250 pounds, and this is going to be times the sine of 55 degrees, because that x component is opposite of that 55 degrees, like it was day 1. Sum of forces in the y direction equals 0. So now I've got, in the y direction, I've got normal minus 250 pounds times the cosine of 55 degrees. So that's 2 equations, 3 unknowns, but remember, we are right at the point where it's just starting to slide. So that means we have reached the maximum friction value. That means we can set it equal to mu sub s times n. Unless I know that I can't set this equal to, I can just have to solve for f and n independently. But since we're at the maximum point, we can set them equal. Okay. So what do we got here? 3 equations, 3 unknowns. This is solvable, correct? Yeah, go ahead and solve it. I've got an answer here, but go ahead and pause it, solve it, see what you get. Got it? All right, this is what I have written down. If you get something different, say so in the comments, check the comments, see if somebody else is agreeing with your disagreement. I'm okay with that. I've not run these numbers through. Okay. And then the friction force, 43.02 pounds. Now, is that what the problem's asking for? What the heck are we looking for? We're looking for W. Well, Steve, why'd we start with this one if we're looking for W? That W's not even on this. I get that. We could have started here. Nothing wrong with that. Let's go there next, right? What am I looking for? I'm looking for W. So I could have started with a free body diagram of W. Now I looked ahead and said, you know what? I can't find anything useful here. I mean, what I can do is I can say, well, what forces are applied to this block out here? Well, the weight and the tension. And assuming it's right at the point where it's in equilibrium, it's just barely starting to move, so it's right at the point where it's just barely starting to break loose, that means this tension has to be the same as the weight. Okay? Well, if that's the case, and I've already found this tension, that tells me the weight is going to be about 247.8 pounds, the same as this tension up there. So about the same weight. And that only happens because I've got 0.3 and an angle of 55 degrees. Notice those are the 2 main parameters that determine this. You know, this weight directly affects the weight of this one block directly affects the weight of this other block required. But other big factors here are going to be the static coefficient of friction and the angle. Because of this combination of 55 degrees and 0.3, then it's roughly the same weight here as it is there. If either of these change, if I put it on a much smoother surface where mu sub s is like 0.03, so really, really smooth surface, then it's probably going to require much less weight to actually get that to move. Probably, if it's a tenth of the friction, it's probably a tenth of the weight. You're welcome to kind of play with those, plug in some different mu sub s and different 55s. And again, if you really want practice here, rework this problem. Don't look at this, don't look at your notes. Rework the problem from scratch and figure out what is the minimum amount of W required to keep the block from sliding down, and see how you do. All right, guys, I'm going to stop there. That's a good set of lectures for friction. You should be okay to get started on the homework, and we'll talk about centroids in the next lecture. I've got 6 pages here, so go back and renumber these guys. 6 of 6, 5 of 6, 4 of 6, 3 of 6, that's 2 of 6, still needs 6, 3 of 6, 1 of 6. I guess I'm still recording right now. All right, guys, talk to you later.